Assalamualaikum everyone. So now we have reached chapter 5, Internet Protocol version 6. Previously we have learned about IPv4. So for the first part of IPv6, okay, first we are going to look at the differences between IPv6 and also IPv4, and then we look packet as well as what have changes from the IPv4 headers to IPv6 headers, and also addressing in IPv6. Right. So IETF, or Internet Engineering Task Force, began an effort to develop a successor of IPv4. Okay. So this is called IP version 6, or Internet Protocol version 6. It is described in request for comments documentation. This RFC. These are the RFCs for the IP version 6, and you can Google these RFCs. It is available freely on the internet. Okay, so the initial motivation is actually because of the lack of space in the IPv4 32-bit address. Okay, remember that IPv4 has 32 bits of address. So they thought that this space is soon going to be completely allocated. Okay, so one of the motivations for IPv6 is to increase address space in order to allow maintaining end-to-end transparency. Okay, it means that to provide larger IP address space, okay, for many more users of the internet. Because as we know nowadays, the increasingly users of the internet, for example, for the use of mobile phone, for the use of the Internet of Things applications towards the Industry Revolution 4.0. So we can imagine that one day soon IPv4 address space will be completely allocated. It means that all users have used this IPv4 address space. So because of that, this is the motivation for developing the IPv6. Okay, and also the designers also took this opportunity to improve other aspects of IPv4. For example, to introduce the quality of service mechanism that is not available on the network layer of IPv4, and also the improvement of the network layer security end to end. Okay, for this IPv6. Right. So what is new in IPv4? Okay. First, IPv4 has completely new header format. Okay. Some of the fields in the IPv4 have been dropped. For example, fragmentation and reassembly. Okay. So IPv6 does not allow for fragmentation at the intermediate routers. So this is a completely different with the IPv4, where in IPv4 at routers and also source, the fragmentation can occur. But for the IPv6, the fragmentation only at the source. Okay, before the packets is being sent to the network. Okay, and also improve the security. Okay, where the confidentiality and integrity of the packet are added. Okay, to the network layer. And also IPv6 has 128 bits of address, which is equivalent to 16 bytes. Okay, so this is totally different with IPv4, in which IPv4 has only 32 bits of address. So you can imagine there is the address space is very large. It's huge. Okay, with the 2 power of 128 for the address space. Okay, so basically the address space is 2 to the power of 128. And also on top of this larger address space, there is also a new type of address introduced in IPv6, which is called Anycast. Okay, so we will have a look later to this in the next slides. And then there are also new options added to the IPv6. So the changes from IPv6 to IPv4 versus IPv4. First, IPv6 supports data integrity and also confidentiality at the network layer. Okay, so there are options, and the new options are added to the IPv6. There are options to add encryption and also authentication. And also IPv6 is designed to handle the transmission of real-time data such as audio and video. Okay, this is by the use of flow label. Okay, so flow label here is added to the IPv6 to enable source to request spatial handling of the packet. For example, to support traffic such as real-time audio and video. So basically, this flow label is just like the labeling of the packets, which belongs to particular flows for which the sender requests special handling. Okay, for example, some of the packets request special handling, okay, in terms of quality of service or real-time service. Okay, for instance, audio and video transmission, it might be treated as a flow that needs this kind of QoS or quality of service. On the other hand, maybe perhaps the more traditional applications such as file transfer and also email might not be treated as this flow, as the QoS flow. And it is possible, for example, that the traffic carried by a high priority user, okay, might also be treated as a flow. Okay, this is possible in the future. For example, someone who's paying for better service for the traffic might also get special treatment for their packets. Okay, another one, the difference between IPv6 and also IPv4. IPv6 has allowance for extension. Okay, for example, it is designed to allow the extension of protocol if required by new technologies or applications. Okay, so meaning that it has at the header, okay, it has an option to allow, for example, new applications to be added to IPv6 or also new technologies. Okay, so a new encoding of option also allows for more flexible options processing, right? So better header format. Okay, IPv6 uses a completely new header format where options are separated from the base header and inserted when needed only. Okay, so this will simplify and also speed up the routing process. Okay, so when it is made optional, so the resulting header will allow for faster processing, okay, of the IP datagram. Okay, just like I mentioned just now, the new options also allow for additional functionalities or maybe for future technologies and also applications. Okay, so moving on to the reasons for introducing IPv6. So like I said before previously, because of the address space issue in IPv4, so the designers thought that the introduction of IPv6 will solve the address space problem. Okay, then this is especially interesting for mobile networks and large growth countries, for example, China. But this is not only for China, but for the whole world, because just like what currently we have now, during the movement restriction order in many of the countries. So can you imagine how many users are using the internet right now? So imagine this, like one day this will be, the address space for IPv4 will be exhausted and there is no more address that could be allocated to a new user. So this is where IPv6 seems very, very useful, that it have been introduced before. Okay, and also IPv6 support of flow labels, okay, for labeling of the packets. For example, certain packets needs priority or need quality of service. Okay, IPv6 also have full support for tunneling and interworking. Okay, for example, like IPv4 network and also IPv6 network. So how IPv4 network is going to be connected to IPv6 network. Okay, so this designer have already thought of the interworking between IPv4 and IPv6. So there are strategies to migrate from IPv4 to IPv6 or for interworking between these two networks. Okay, and also how IPv6 wants to work over the v4 networks. Okay, over the version 4 network. Also, the designers have already thought on this and have come out with several strategies. However, for IPv4 over v6 network, it is not defined yet, which is not needed yet. Okay, and there are also several reasons for not introducing IPv6. It means that why are we going to use IPv6 when IPv4, for example, can give us now enough address? Okay, first, because when one system is going to use IPv6, it needs changes to all routers and also end system, because all of the addressing have changed from 32 bits to 128 bits. So can you imagine the changes required to all these systems? Okay, and also changes required to some applications. So this is somehow a tedious process. So not all designers or not all users are intrigued to use this IPv6. Okay, and also IPv4 works well so far, and also they have come up with several also strategies on how to, instead of for example, on how to allocate more addresses to IPv4 users. Okay, so besides subnetting, there are also several strategies that can be used, which we will learn in the next chapter. Okay, because we want to reuse the IPv4 addressing. Okay, to avoid the exhaustion of the IPv4 address space. Okay, and also IPv6 have very long address. Okay, so it will introduce enormous overhead, especially for short packets. So can you imagine a short packet that that needs to be sent, but it has somehow longer addresses, okay, compared to the content of the packet itself when using IPv6. So this is one of the reasons why people are not keen of using IPv6. And also, people also thinks that the addressing problem is not as urgent as believed 5 years ago, because people keep on having or keep on proposing a solution to somehow to solve the IPv4 workspace problem, okay, space problem. So because of that, they don't think that it's a need to use IPv6, okay, because previously it was predicted that all hosts in the world will be using IPv6 in 2010, but it's not happening yet. 10 years after 2010, it's still not happening that all systems are using IPv6. And you can also find out from the Google on how many countries have already changed to IPv6 and how many percent users in the country have changed to IPv6. You can Google the information, okay, to know. There are certain countries, especially Europe, also US, have changed to IPv6. Okay, but somehow for others, there are other solution for the problems of address space in IPv4, for example, using subnetting, or also dynamic address allocation using DHCP, and also using NAT, okay, which we will learn in the next chapter. Okay, so let's look at the IPv6 packet header changes. Okay, you can see the purple box here is the one who have been modified, okay, from IPv4 version to IPv6, and the orange box here shows the orange boxes here show the fields that have been deleted, okay, that have been deleted. For example, header length, identification flags, fragment offset, header checksum, and also options. Okay, so basically if you see at the basic structure of IPv6 is actually simpler than IPv4, right? Okay, so the header changes at IPv6, okay, for example, there are some of the fields that exist in IPv4 but have been removed in IPv6. For example, header length, identification, flag, and offset fields, and header checksum. Okay, so header length is eliminated because the length of the header is fixed in this version. So we don't need this header length. Okay, the identification, flag, and offset fields are eliminated from the base header in the IPv6 because these are now included in the extension header in terms of fragmentation. Because remember that for IPv6, the fragmentation is only at the source. So this is not needed. Okay, at the intermediate nodes or intermediate routers, they can they cannot perform any fragmentation process. Okay, header checksum is also eliminated because checksum is provided by the upper layer protocol, for example TCP or UDP, so therefore it is not needed at this level. Okay, so some of the fields change from IPv4 to IPv6. okay, at the headers. For example, service type in IPv4 fields have changed to traffic class plus flow label. Okay, so traffic class and flow label work together to take over the function of the service type field in the IPv4. Also, total length is eliminated in IPv6 and it is replaced by payload length fields. Payload length means the data field length, okay? Because previously in IPv4 we need to know the total length and we need to know the header length, and from there we can get the total payload length, okay? But for IPv6 it is clear, the header length is fixed, so the only things that we need to know is the payload length, okay? And then time to live here is also similar with IPv6, but it is now called hop limit. Okay, it is the same. It performs the same function as time to live in IPv4. Okay, so protocol field is replaced by the next header field. Okay, and also there is a new extension headers introduced to IPv6. Okay. This is actually options in IPv4, but it is implemented as extension headers in IPv6. Okay, for example here, fragmentation. Fragmentation here replaces flags and also fragment offset fields here. Okay, use next header field. Okay, so this is to give basically the length of the base header is fixed at 40 bytes, but there are also extension headers that can be added to IPv6 to give more functionality to the IP datagram. Okay, so this base header can be followed up by 6 extension headers. Okay, so many of these headers are put as options in IPv4. Okay, so we have a look at the IPv6 header. So the base header here is 40 bytes. Okay, so we see here 40 bytes come from this. Okay, for example here we have 32 bits, which is 4 bytes. Okay, in the first line here 4 bytes. Second line also 4 bytes, and for the addressing, for the source address 16 bytes and destination address 16 bytes. So which these boards here should be longer. Okay, so 16 plus 16 plus 4 plus 4, so the base header here is 40 bytes. Okay, and the payload here up to this bytes, Ch5 535 bytes. Okay, so there are options for the extension header as well. Okay, so we have a look at the fields for IPv6 one by one. Okay, so this is the version. Okay, so it defines the version number of IP for this IP datagram. So there are 4 bits for this version. Okay, so for IPv6 the value is clear, which is 6. Okay, so traffic class. So traffic class takes 8 bits, and this field is used to differentiate different payloads, okay, with or different data with different delivery requirements. Okay, so it replaces the service class field in IPv4, and this is flow label. So flow label takes 20 bits field. Okay, it is designed to provide special handling for a particular flow of data. Okay, in other words, it can be used to speed up the processing of a packet by a router. So when a router receives a packet, okay, instead of consulting the routing table and going through a routing algorithm to define the address of the next hop, we can look at the flow label table for the next hop. Okay, we can also say that this flow label can be used to support the transmission of real-time audio and video. Okay, so basically that are the function of the flow label to speed up the processing of the packet. Okay, the next one is the payload length. Okay, it takes 2 bytes. Okay, so it defines the length of the IP datagram excluding the base header. Okay, so only the data, excluding the base header, which is 40 bytes. Okay, and the next one is a next header. Next header is 8 bits field. Okay, it defines the header that follows this base header. Okay, so I repeat, it defines the header that follows this base header in the datagram. So the next header is either one of the optional extension headers here, okay, used by the IP here, or the header of an encapsulated packet such as UDP or TCP. Okay, basically it identifies the protocol to which the contents of the data of this packet is going to be delivered. For example, TCP or UDP. Okay. So each extension header also will contain this field. Okay, basically this field in version 4 is called the protocol. Okay, the next one is hop limit. Okay, it serves the same purpose as the TTL field in the IPv4. And finally, the source and also destination address, which each takes 16 bytes. Okay, 16 bytes in the packet header. So this internet address, they identify the source address for the datagram, and this one destination is for the destination of the datagram. Okay. However, if source routing is used, this will contain the destination address will contain the address of the next router. Okay. So after this, I will explain what is the meaning of the source route. Okay. So basically, this is what I have explained before. So you can read one by one the explanation on the IPv6 base header. Right. So this is the extension header, okay, which can follow the base header. So it serves to give IPv6 more functionality. Okay. So there are 6 categories of extension header. So the first one is hop by hop. Okay, hop by hop is used when the source needs to pass information to all routers visited by the datagram. Okay, for example, some of the routers need to be informed about certain control function or management. Okay, or if the length of the datagram is more than usual, 65,535 bytes, so routers must have this information. And this destination is also one of the options. It used when the source needs to pass information to the destination only. Means that intermediate routers cannot have access to this information. Okay. And source routing. Source routing means that, for example, previously we said that the destination address is the final destination of the datagram. But for source routing, the destination address changes from router to router. Okay, so in source routing header, it has a list of addresses that the datagram must visit. It means that the source have already determined which route to take and which routers to be visited by that datagram. Okay, for the fragmentation, in IPv6, only the original source can fragment. Okay, so a source must use the path MTU discovery to find the smallest MTU supported by the network, by any network on the path of that packet. Okay, so we will have a look in the next lesson for the fragmentation of IPv6. And the next one is authentication. Okay, so the authentication, first it validates the message sender, and also the second one, it ensures the integrity of the data. Okay, so it is needed so that receiver can be sure that this message is from the genuine sender and not from any imposter. Okay, or it needs to check that the data is not altered in transition by some hackers. So basically, it wants to provide more security to the packet. And ESP here means the encrypted security payload. Also, security extension. Okay, it provides confidentiality and also guards against eavesdropping. Okay, means that they don't want anyone in the on the way from the of the packet from the source to destination to eavesdropping or to listen to that packet. So this service is provided by this ESP as the extension header for the IPv6. So this is the example of extension header. Okay, for example, we have the IPv6 header. Okay, and the next header here is defined as TCP header. But here, the next example here, if we have IPv6 header, and the next header here, we want to put the routing header. Okay, the source routing header. Okay, and after that, we put TCP header in the next header field. Okay, and in the next example, if we want to put 2 options of the extension, which is source routing and also fragment header. So we put together this routing and also fragment header, and then the next header field, which is, okay, moving on to the IPv6 addressing. Okay, so for the IPv6 addressing, I have said before that it has 128 bits. Okay, so it is very, very long if we put it in terms of binary number. Okay, it has 16 bytes. Okay, if binary number, it needs to have 128. For bytes, it has 16 bytes, and it will be shorter if we use hexadecimal digits, which is 32. So to make addresses more readable, IPv6 has specified colon hexadecimal notation. So this is a colon hexadecimal notation, or colon hex for short. So in this notation, 128 bits here are divided into 8 sections. Okay, so 8 sections with 2 bytes each. Okay, in length, 2 bytes each. Okay, 2 bytes in hexadecimal notation require, for example, here is 2 bytes, so it requires 4 hexadecimal digits. Okay, so therefore the address consists of 32 hexadecimal digits, with every 4 digits here separated by a colon. Okay, so here all in between 4 digits of hexadecimal, it is separated by a colon. So these addresses can be further abbreviated, or in other words, can further be shortened. Okay, and IPv6 address also supports CIDR notation. Remember that we have learned in IPv4, CIDR means classless interdomain routing. Okay, with slash notation, it also supports that. So addresses here are assigned to individual interface or nodes. Okay, not the nodes themselves. And also it can combine long and also multiple addresses per interface to improve routing efficiency. Okay, so moving on to the abbreviated address. Okay, let us see how the address of IPv6 here can be shortened. Okay, so we know that it is very long if we put in terms of full IPv6 address, but somehow, even in this hexadecimal format, many of the digits are still zeros in IPv6. Okay, in this case, we can shorten the address. Okay, for example, here, the leading zeros can be omitted. Okay, can be eliminated. For example, here, FDEC, you can put FDEC, BA98, BA98, 0074. So 00 here is the leading zeros. Okay, so it can be omitted. So we put it as 74. Okay, so remember also to put the double colon here. Okay, 3210, 0 at 3210 here cannot be omitted because it is not leading zero. It is a tail zero. Okay, means at the end of the numbers here. So we still put it as 3210. And 000F also, 3 zeros here are leading zeros, so we can put it as F, BBFF, BBFF, and 0 here we can just put 0, okay, only 1 0, and FFFF. Okay, so only zeros can be omitted or can be shortened. Okay, we can also further put we can also further abbreviated or shorten the address. Okay, we call it zero compression. Okay, can be applied to colon hex notation if there are consecutive sections consisting of zeros only. So this is another example, right? Not the same example as this. Okay, so this is another example. We have many zeros, okay, in the address of IPv6 in between the hexadecimal digits. So what we can do is actually we can remove the zeros. We can replace it with only consecutive double colons. Okay, for example here, this 4 zeros, we can just put dot, 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 okay, which is double colons. Okay, so we can replace it with double colons. But remember that if there is another example, for example, there's another 0 at the end here, we can only put double colon once only. Okay, we cannot put twice. Okay. Okay, let us see another example for the IPv6 address. Okay, if we can see here, the IPv6 address has, for this example, has several zeros. Okay, sorry for the bad handwriting. So we can abbreviate this address. Okay, we can choose only this part of zeros or this part of zeros to replace it with double colons. Okay, so for this example, we choose this part, okay, and replace it with double colons. But for this part, okay, for these zeros, we have to put it zeros, okay, because you can choose only one. Okay, you can use only once this double colon in an IPv6 address. You cannot put this double colon and this double colon, it is not permitted. Or you can choose this part, okay, to make it to replace it with double colons, and for this part you still have to write zeros. Okay, so this is an example for the abbreviated address. Okay, besides abbreviated address, IPv6 address can also represented in terms of mixed representation. Okay, this can be used during the transition period. For example, we put IPv4 address in is IPv6 address. Okay, we embed this IPv4 address in IPv6 address. So this is the example. So what we can do here, we put the IPv4 address. Okay, we put the IPv4 address which is as the rightmost 32 bits. Okay, and then the balance 128 minus 32 bits we put in terms of hexadecimal digit. Okay, it means that we use the colon hex notation for the leftmost section, and for another 4 bytes we use dotted decimal notation. Okay, so this happens when all or most of the rightmost sections of the IPv6 addresses are zeros. Okay, if this part of the IPv6 address is 0, we can replace it with IPv4. Okay, right. So during the transition from IPv4 to IPv6, hosts can use IPv4 addresses and embed in IPv6 addresses. Okay, so this is for the migration purposes. Two formats have been designed for this purpose, which is compatible and also map. Okay, for map address, for compatible address, it is an address of 96 bits of zeros followed by 32 bits of IPv4 address. Okay, it is used when IPv6 host needs to send message to another IPv6 host through IPv4 network. Okay, for example, we put this IPv4 address, okay, as IPv4 address which is 32 bits, and others are all zeros. Okay, all zeros. So what we can do is we put IPv4 address here as the hexadecimal digits, and others here we can put the zeros here, we put here, and this one is the double colon to replace these consecutive zeros. So again, it is used when a computer using IPv6 wants to send a message to another computer using IPv6, but they have to go through a region where the networks are still using IPv4. So the sender here must use IPv4 compatible address to help the transmission of this packet to the IPv4 region. And also it is used for devices compatible for both IPv4 and IPv6 address. Okay, so this IPv4 address also must be globally unique IPv4 unicast address. Okay, unicast address. However, this compatible address for IPv6 is now deprecated. Okay, means that not many favor this method because of the current IPv6 translation mechanisms, which is no longer use these addresses. Okay, so there are other migration strategies that can be used to use both IPv4 to solve this problem when IPv6 host needs to send message to another IPv6 host through IPv4 networks. Okay, it is still usable but regarded as obsolete, and it can best be avoided because it has been superseded by another method. Okay, but we still learn it in our lesson here. So this is an example of the compatible address, how it relates with the IPv4 address. So this is actually the IPv4 address. Okay, this part is actually the IPv6 address. So this IPv4 address is in hexadecimal digit. So if we put it in terms of binary number, we can see that 0, 2 here is this part. Okay, if we put in the binary digits, okay, from hexadecimal to digits, this is to decimal. Okay, 0D here is in hexadecimal, this is in digit, and this is in decimal. Okay, so you need to know how to convert between these different numbering system, hexadecimal to binary and also to decimal. Okay, so moving on to another type of address, which is map address. In map address, you also put the IPv4 address. However, for IPv6 part, it comprises of 80 bits of zeros followed by 16 bits of 1. Okay, so here are 80 bits of zeros and here are 16 bits of 1, and this is IPv4 address. So it is used when IPv6 host needs to send message to IPv4 host through IPv6 network. Okay, previously for compatible from IPv6 to IPv6 through IPv4. But for this one, from IPv6 to IPv4 through IPv6 network. Okay, so this is used also for IPv4 device that is not compatible with IPv6 into the IPv6 address space, right? So again, it is used when computer that has migrated to IPv6 wants to send packet to a computer that is still using IPv4. Okay, so the packet travel mostly to IPv6 network, but finally delivered to IPv4 host, right? So for this part of the address, IPv4 address, it is changed to the hexadecimal colon format. Okay, just like compatible address before. Okay, so finally, there are several types of IP addresses that can be used in IPv6. For IPv4, we know that we can use unicast and multicast, but for IPv6, it has introduced one more categories of address, which is anycast. So to recall, for unicast, it defines a single computer, and a packet sent to unicast address must be delivered to that specific computer. Okay, means one-to-one addressing. For multicast, it defines for a group of computers, a packet sent to a multicast address is delivered to each members of the group. That is multicast. Okay, so this is one-to-one, this is one-to-many in the group. But for anycast, it defines a group of computers with addresses that have the same prefix. So a packet sent to an anycast address must be delivered to exactly one of the members of the group. Okay, it means that it can be delivered to any one of the members of the group, not all like multicast. Okay, so basically, this is unique to IPv6. The anycast is unique to IPv6. So that is basically all about the IPv6 addressing and also the format header. So we will meet again in the next lesson. We will have a look at the ICMP version 6 and also the fragmentation of the IPv6 as well as the migration strategies from IPv4 to IPv6. Thank you.